When you're solving problems in chapter 12, you're always reading the problem, and it's associated with mixtures or mixing. And the first thing you do when you read the problem is you ask yourself, am I given the mass fraction or the mole fraction as the given information in the problem? So I want to give you some ideas just to start on what is a mass fraction and what is a mole fraction and how are they different. So that's really a key is once you start reading this problem, the first thing you ask yourself is, do I have the mass fraction or do I have the mole fraction? You get one or the other of those. And so what are they and how are they different? And what I'd like to do is I'm going to define what is a mass fraction, what is a mole fraction, and then just breeze through some, quickly reading some problems right out of the textbook so that you can quickly learn how to decide which do I have, mass fraction or mole fraction? What are the key solution approaches or both? How to calculate mole fraction, for example. So this is sort of the formal definition of mass fraction and mole fraction. What they did, they apply to a mixture of constituents, commonly a mixture of ideal gases in chapter 12. However, do recognize that constituents can be in any phase. So example, salt water, ocean water is a mixture of water, H2O, and salt. NaCl. So that's also a mixture. But in chapter 12, we're going to be dealing primarily with ideal gas mixtures. So the first is what's mass fraction? What's the variable? In my world, I call it MF sub I, mass fraction sub I. And so each constituent I will have its own little mass fraction. And so recognize that in a mixture, the sum of all the mass fractions must add up to 1 or 100%. So you see here in the definite, the sum of all the mass fractions must equal 1 or 100%. Okay, mole fraction. So this is going to be getting back to either high school chemistry or freshman chemistry in college. What's a mole fraction? And so in the textbook and in my world as well, the mole fraction is depicted by the variable y sub I. That's a mole fraction. That's a number less than 1, bigger than 0. Okay. And so for a mixture, the sum of the mole fractions has to add up to 1.0 or 100%. So similarly, the sum of all the y sub i's in a mixture has to be equal to 1.0 or 100%. You get the idea. Okay, and so freshman chemistry review. I'm hoping you're thinking back about mole fractions that you covered either in high school or freshman chemistry. And you recognize that in a problem statement, if you were given the volume fraction of each constituent, that's exactly the same as saying the mole fraction. And so in an example of a problem, a volumetric analysis, some commercial analytical services provided you a volumetric analysis of let's say, some type of gas. It says the volumetric analysis is nitrogen 60%, oxygen 30%, and CO2 10%. So a volumetric analysis, that's the same as the mole fraction. And so what's given in this problem would be Y, the mole fraction, Y of N2 is 0.6, Y of O2 is 0.3, and Y of CO2 is 0.1. You add them all up and you see that they equal 1.0. Simple as that. The next thing in chapter 12, as you read through your textbook, section 12.2, you're going to encounter a model for ideal gas mixtures called Dalton's model. And Dalton's model introduces the idea of partial pressures. And you may have heard that jargon before. You might not have. That's okay if you haven't. But a partial pressure is derived from Dalton's model for mixtures. And the partial pressure is a pressure property of each constituent not the mixture itself. And so, for example, in the book will call P the pressure of the system. So capital P or little p. So here in this equation 1212, here's P over here on the right side of the equation. In my world, that's capital P, and I call that P of the system. So, for example, atmospheric air, the pressure of atmospheric air would be 1 atmosphere or 101 kPa or about 1.01 bars. So that's the pressure of the mixture of our air. But each constituent, the nitrogen and the oxygen and the argon, will have its partial pressure, and we call that, each of those partial pressures is called P sub I. And so recognize here, and so how do you define the partial pressure? The partial pressure of the ith constituent is simply the mole fraction times the pressure of the system. So you get that? That's the key definition. That's equation 1212. That's the definition of partial pressure. The mole fraction of the constituent times the system pressure, what you measure with a pressure gauge. So recognize that the pressure of the system in your textbook, P, I call it P system, equals the sum of all the partial pressures. System pressure equals the sum of all the partial pressures in your mixture. So let's define your system for a mixture. So do you see that a system can either be a closed system or an open system? A closed system, what's contained in a piston and cylinder? What's contained in a rigid vessel? An open system, that would be the mixing problem, wouldn't it? An open system where you might have two inlets, let's say nitrogen and CO2 being mixed together, two inlets, and one outlet would be the mixture of nitrogen and CO2. So recognize closed system would be a fixed mass with two or more constituents in it, two ideal gases. The system pressure would be described as P in your textbook, or in my world, P of the system. And the sum of the partial pressures must equal the sum of the partial pressures equals the system pressure. You might have an open system, the mixing problem. You might have multiple inlets and one outlet, or you might have a couple of outlets. Each stream might be a single constituent or a mixture of constituents. But recognize that partial pressures apply to each stream based on each stream's system pressure. Let's get a little practice reading problems quickly without solving them. So textbook problem 12.2, it says, let me move my picture. It says the analysis on a mass basis of a gas mixture at 40 degrees F, system pressure 14.7 psi, is 60% carbon dioxide, 25% carbon monoxide, and 15% oxygen. Okay, and so determine blah, 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 blah. Mass basis. So that says the mass fractions are given. And so for this particular problem, the mass fraction of CO2 is 0.6, mass fraction of carbon monoxide 0.25, and mass fraction of oxygen 0.15. So if within this system, let's say you had 10 kilograms of this mixture, 10 kilograms, you'd have 6 kilograms of CO2, 2.5 kilograms of CO, and 1.5 kilograms of oxygen. So you can see how the words in the problem tell you what your given information is. Okay, here's another problem. We'll breeze through it. It says a mixture of 5 kilograms of hydrogen and 4 kilograms of oxygen is compressed in a piston and cylinder. Closed system, polytropic process, ends 1.6, find the heat transfer, change in entropy. Well, what's given in this problem? Well, mass is given of each constituent. So do you see that in your head, you can determine the mass fractions, can't you? Well, let's see. Just by inspection, how many total kilograms do you have in your mixture? 9, 5, and 4. So the mass fraction of the hydrogen is going to be 5/9. and the mass fraction of the oxygen is going to be 4/9. Now, I didn't do the math because we're not going to be solving through this problem, but do you get the idea? So your first job, your first step in these chapter 12 problems is thinking about what am I given in the problem statement, and do I have mass fraction or mole fraction, and can I determine it from the given information? So this one's easy, right? You're basically given the mass fractions because you're given the mass of each constituent. Okay, here's a problem 1217. Natural gas has a molar analysis or a volumetric analysis of 60% methane, 40% ethane, and it enters a compressor, blah, 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 and you're asked to solve this problem. So when you read through, it says molar analysis. That means you're given the mole fractions. So the methane mole fraction Y of the methane is 0.6, and Y of the ethane is 0.4. So again, it's kind of like falling off a log, but just want to get you familiar with reading these mixture problems and see where do I go, what's given to me. Example problem 4 is 1224 out of the textbook, and it includes a sketch. And I see we've got 2 inlets and 1 outlet. That's an open system, isn't it? It's open system. It's a mixing problem where we're mixing argon and carbon dioxide. And what's coming out is a mixture of argon and carbon dioxide. Okay, can you figure out what's given in the problem? Do you see that here's a mass flow rate 1 kilogram per second and a mass flow rate of 0.5 kilograms per second here? Okay. Do you see here that in solving this problem, well, this is the mass fraction of this constituent is 100%, right? It's pure argon. Over here, part 2, CO2, it's 100% CO2. But here, let's see, what have we got? We've got 1.5 kilograms per second coming out of this mixture. So do you see that the mass fraction of the argon coming out here would be 1 divided by 1.5? And the mass fraction of the CO2 coming out here would be 0.5 over 1.5. So in this, the mass fractions are given. You can figure out the mass fractions without being explicitly told what they are. So you get the idea? Another example problem, a gaseous fuel with a volumetric analysis of 60% methane, 30% hydrogen, and 10% nitrogen is burned to completion with air. Well, so what's given? So the fuel, what's given with the fuel? Volumetric analysis, that's the mole fraction is given for the fuel. So Y of the methane, CH4 is 0.6. Okay. Y of the hydrogen is 0.3, and Y of the nitrogen is 0.1. So volumetric analysis, same as mole fraction given. Now looking ahead, you're going to be looking for R for a mixture. Okay. So let's remember, let's do a little refresher on what is R. R is the gas constant for any ideal gas. And why do we use R? Well, because we use the equation of state. If it's a closed system, PV equals mRT. For open systems, P times little v is equal to RT. Those are identical statements. And so you can look up R bar. Hopefully you've got it in your head, or you can look it up. R bar is the universal gas constant, and they're tabulated here on the screen. Okay. And so you can either look those up or you have them in your heads. And so you should know many of these gases, the molecular weight of each gas. Hopefully you've got those in your head, or you can look them up. And so do you see that R for any constituent is simply R bar over the molecular weight of that constituent? And ultimately, you're going to be using the mass fraction to determine R of the mixture. Okay, there we go. That's the introduction to the next slide, isn't it? Ultimately, we're going to need R for the mixture. And if we have a first law problem, we're going to need CP for the mixture. Well, how are we going to use that? Why do we want it? Why are we looking for R of the mixture? It's because we need to go right back to the familiar fundamentals, the ideal gas equation of state. And instead of having a big accounting problem for all these constituents, we'd like to just treat the mixture as one single ideal gas. So that's why we need R of the mixture. And so how will you get that? Well, let's see. R of the mixture is simply going to be the sum of the mass fractions of each constituent times R of each constituent. Simple as that. Okay. Similarly, so you got that? So that's why you need mass fractions. If you're not given mass fractions, you're going to need it. Okay. And multiplied by R, kilojoules per kilogram degree K, or foot-pounds force per pound mass degree R for each constituent. Same idea for CP of the mixture. If you're specific heat, if you're looking for CP of the mixture, you simply are going to sum up the mass fraction of each constituent times CP of each constituent that you have looked up in your basic tables. You have good experience so far. I hope you get the idea. That's why it's so convenient once you understand the problem statement to kind of move quickly to determining R the mixture and or CP of the mixture, depending on the specific problem you have. Okay, the recap of definitions. A mass fraction commonly used for continuity equation balancing in mixing problems and the first law. Mass fractions, because remember, mass is conserved, not moles. Mass is conserved. Mole fraction, same as the commonly used volumetric analysis. It's very common in the engineering world, in the working world, to see the words volumetric analysis, and the engineer immediately says, "Oh yeah, that's the molar analysis," or in other words, the mole fractions are given. And so, why do you need to do that? You say, "Oh, I shouldn't have to worry about that." You definitely are going to need to use mole fractions when you are determining the partial pressure of each constituent. And that's going to be important in your problem solving. Understanding partial pressures will be important in solving these mixture problems. Hope that helps give you an idea of what's the difference between mass fraction and mole fraction, and getting a little experience in reading a problem and understanding which do I have, which is given to me. A lot of times that's a big hurdle to get over, and that can get you started solving your problem. So next video, I'm going to show you how to interchange mass fractions and mole fractions, because it's very common that you're given one, but you need the other to solve the problem. That's a very common situation.